let's start our lecture number 13. And in this lecture, we will solve boundary value problems involving more than one dielectric. Obviously, there are simple problems involving more than one dielectric. Problems that having high symmetry. Okay, for instance, I can have just I can have a sphere, a conducting sphere. Okay, with a given charge, let's say. Then I can put a layer of a dielectric around it. Can put another layer outside, right? Can keep putting layers outside, concentric shells, let's say, thick shells, no longer shells, just and then I can keep doing that, and they have an epsilon 1, epsilon 2, let's say vacuum outside. So I have a problem with multiple dielectrics. We want to know the field distribution in the different layers. Okay, we can solve those problems. It's very simple to solve. It's a matter of solving Laplace's equation in each region here, right, and matching boundary conditions. That can be solved. We want to consider problems in which we don't have just simple one-dimensional dependence of the potential. Okay, so that's the type of problem we are talking about. So that's the context of this lecture. I mean, you're going to do some problems involving more than one dielectric in which the potential is not a simple, straightforward one-dimensional potential solution. We have been using in a number of situations the symmetry property of the Green's function. We are not obliged to use the symmetry problem to solve the problems. I'm going to show you today that we can avoid using that property to solve a problem. Okay, but it's important to see in what situations Green's function is symmetric indeed, right? So we are going to make a proof of the symmetry property. Let's see what type of BVPs this function has a symmetry. And finally, we're going to show you how to solve the method of images involving more than one dielectric. You are going to have a point charge in one dielectric, then you have one type of surface that separates this dielectric to a neighbor dielectric. Then how would we solve this problem? Okay, we are going to do an example for a planar boundary, but we can do different situations. We can have a point charge here, a spherical dielectric, or a charge line parallel to a plane or to a curved dielectric. We can solve all these problems. Okay, so they're going to outline and show you what's the general method of solving it. Okay. Basic reference for this class, there's some typo here, is Jackson section 4.4. Even though Jackson doesn't solve the image method the way we do, he do as different authors do. He just assumes fictitious image charges and solve it. We are going to show how those charges arise in our formulation. Okay, we're going to demonstrate how they arise. The first problem we would like to talk about is the boundary value problem, in which we have one dielectric sphere which is placed in a region in which you have an originally uniform E field. So you have a region in space. Let's say you have a gigantic capacitor, parallel plate capacitor. Okay, so have two electrodes energize it, and have a very large capacitor, then you have a uniform field. Or you can have a small capacitor, and you can consider that you have a uniform field, let's say, at the center of the capacitor. Then what happens if I suddenly put a dielectric in this region, right? Sorry about that. Put the dielectric here. So obviously the dielectric, the field is going to interact with the dipoles, right? So it's going to induce surface polarization charges on the surface of the sphere, and we are going to have some curving of the field. So the field is going to curve, right? Something like this is going to happen. So it's like, it's like the field is pulled to the inner part of the sphere, right? That's the problem we want to solve. How high is this pulling effect? How concentrated is this effect? How much energy is pulled inside of the sphere? So this in fact is a boundary value problem. That's how we depict the problem. We have a outside that's assumed that you have a vacuum, and you have a sphere that has a permittivity epsilon, radius a. Okay. So we have a kind of Neumann boundary value problem. We are going to identify it. Okay. So we have to break the problem in two regions. The inner region, the dielectric region, and outside have region 2. I'm finding strange some letters here. What is this B doing here? Well, I'm finding funny some letters that are here. This is supposed to be Z-axis, not B. Okay, sorry about that. And we have a constant field along the Z direction. So we're going to break this into problems, region 1, or region 2. In both regions, you have a potential that satisfies Laplace's equation, right? Like this. And we have a boundary value at infinity. The potential doesn't vanish in this example. The potential has to be such that the field has to be, constant, far away from the sphere. So, what happens is that the sphere disturbs the field near the sphere, but as we go away, the disturbance becomes small, and you have a constant field. So the boundary condition is that the potential outside goes through a behavior that gives a constant field. And you can, so if limit of the potential as Z goes to infinity, let's say limits as magnitude of Z goes to infinity of phi 2 has to be such that the gradient of phi 2 in the limits, which equals to minus E, right, equals to minus E0 AZ. So in other words, the potential can only have one dependence that gives only a Z component of field. Potential has to depend only on Z as for large Z. So this means that the limit as Z goes to infinity of phi 2 is something that the derivative converges to minus E0, right? So we know the derivative is given at infinity. So we have a Neumann boundary value problem. So we can use any function that satisfies the relation here. One particular function is the linear function, right? I can add a constant if I want to, but I mean the constant is going to disappear on derivative. So I can specify that at infinity, potential is simply a linear relation of the form minus E0 z. So that's the behavior of the potential at infinity. Sorry, I'm not looking at my notes here. Let me find it right there. So the potential at infinity has this behavior, so I can use this, this behavior here. So notice also that potential, notice that in spherical coordinates, right? Spherical coordinates at a distance r and at an angle theta from z-axis, z equals to r cosine theta. So in fact, potential limit, right, as z goes to infinity, equals to r times minus z0, right, r cosine theta. So you see that for this problem, the potential depends on two variables. Depends on r and on theta. Right? Doesn't depend on phi. We have azimuthal symmetry. So, so it means that the potential can be expanded as a power series that involves r powers of r together with Legendre polynomials, right? That's the way we expand, inside or outside, right? That's the inside solution. We have two specific constants, A and B, right? And outside we have same behavior, specific constants. Recall that we have r to the L and r to the minus L plus 1. Then we have our physical considerations. Potential is finite inside, in the origin, at the origin, sorry. The asymptotic behavior of the potential is this one. We just said that, right? We just demonstrated. Potential has to be something like this for r very large, right? Then we have two additional boundary conditions on the sphere. Go to the sphere, right? Sorry. Make a nice round here. If you go to the sphere, you have to match the potential at r equals a. Potential is continuous. Right? And there's another condition, which is normal d dr inside, right? Dr is continuous, right? Because we don't have surface charge densities. So we have dr continuous. So dr, recall dr equals to is equals to epsilon er, and by its er is the normal component, radial component of the gradient. It's going to be minus epsilon d phi dr in either side. So I have to match the product epsilon times derivative in each side for solution 1, solution 2 at r equals a. So notice that we have a double infinity quadruple infinity, in fact. We have 4 constants times an infinity. We have an infinity discrete set of constants, right? But recall that when we equate two expansions, each term of the expansion on each expansion has to be equal to the other one. So if we go to this condition that the potential is finite at the origin, you have to eliminate this part of the solution because that's the one that diverges, right? So we have to eliminate that. So it means that we have to set dl equals to 0. Okay? The asymptotic behavior of the potential for large R, we have to make sure that this function here, the limit of this function is exactly minus E0R cosine theta. So recall that cosine theta is the Legendre polynomial of order 1. Okay? So it means that we have an expansion on one side, and we have only one term on the other side. You can look at this one as an expansion, but with only one term. It means that we have to match both expansions term by term. So it means that L equals 1 term here is equals to that one, which is minus 0, and L not equals to 1 equals to 0. So we have another condition. So for L different than 1, then we have a situation in which we you see that independent of R, we have a function of R. Okay, let me just make it very clear, right? We're going to have something like this: CL R to L plus DL R raised to minus L plus 1 equals 0 for large R, right? But this is a function of R. So the only possibility of this function to be 0, whatever value of large R we use, is that we set CL equals 0, DL equals 0. There's no way. But this is only for L larger than 1, right? L equals to, we don't have L equals 0, L different than 1. Sorry about that. L different than 1. Including L equals 0. So L, so there's only one term in the expansion on the expansion, which is L equals to 1. So for L equals to 1, if you go here, I have C1 R to the first power, right? Plus D1 R to minus 2 has to converge to minus E0 R. So this term goes to 0 because 1 over R squared goes to 0. So we have to have C1 equals to minus E0, right? That's what we have to have. So it means that we have determined one constant here. So the potential has one unknown has to be determined, one constant to be determined, right? For the function inside, we have this behavior here, right? The constant that has negative power has been eliminated. We have an infinite discrete set of constants, again. So we have to apply boundary conditions at the spherical surface. One is continuity of the potential function. The other is the continuity of the normal component of the density flux density vector, right? Then we have this second equation here. So one is this equation A, the second is equation B, given here. We're going to define this relative permittivity of the spheric material as absolute relative. So when you plug the expansion and equate, so that's the potential inside at R equals to A. There's the potential given by the function outside at R equals to A. And then we have, we can rearrange, right? We can arrange terms. We're going to have A1A. In this term here, I can put together, we're going to come here. And for L different than 1, we have all these terms here, okay? So again, we have we are seeing that we have an expansion here. I mean, expansion in terms of PL cosine theta, and we are seeing that the expansion is 0. The only possibility is that we set each term of the expansion equals to 0, so this term has to be set to 0, and all the terms AL with L different than 1 will be 0 as well. Okay? So that's what we get. Have this one equation here, right? This came from that one. And all the remaining terms are on 0. Just notice that I didn't put back my microphone, so sorry about that. But I think it's going to be a little bit bad quality for a couple of minutes, for 15 minutes I think, but now it's going to be better. So the potential inside now is A1R cosine theta, right? So for the condition B now, just using one term of the expansion, then we have the second linear equation. So we have two equations, two unknowns. Unknowns are A1 and C1, right? And D1. I mean, you just have to determine two constants with two equations, A1 and D1. You have to determine these two constants. So you do that little work, and we obtain these results. We have this result of the solution of the linear system of equations, okay? And then we have the final solution for the potential inside. We have this, I mean, the solution inside is like this. But recall that R cosine theta equals to Z, right? So inside the potential, if we express the potential in terms of rectangular coordinates, the potential depends only on coordinates. And outside, the potential has a term that has a R cosine theta, and has a term that goes as 1 over R squared. So the potential outside has that linear behavior plus that 1 over R squared term. So I mean, if inside the potential is that due to a uniform field, because gradient of this function is a constant vector, right? If you calculate the gradient, you have the field inside, which is constant. I mean, outside you have a uniform field. You put the sphere distorts this field, but inside the field becomes uniform. So that's what we get. That's a nice result, right? Every time you put dielectric sphere or magnetic sphere as well in a magnetic field. We're going to show that. But this is the same problem, it's very similar. Or a dielectric sphere in a previously uniform field. The field inside of the sphere is uniform as well. Well, notice also that outside the field is that due to the applied field plus a term that gives the distortion. What is this distortion? Well, just notice that a potential that depends on cosine theta inversely proportional to the square of the distance is a dipole type potential. Is that to a point dipole? It's a dipole field. Okay. Recall that a dipole has a potential, a point dipole, right, at a distance r and at an angle theta relative to the dipole axis. Oh man. Has a potential which is P dot AR, which is the versor, unit versor, right? AR, 4 pi, this is epsilon 0 r square, and if you break that, it's going to be dot product is P cosine theta. Sorry. So that's the potential. This term this is the term that gives the distortion in the field, that curves the field. This term is negligible away, very far away from the sphere, but has some important effect close to the sphere. And that's what makes the field lines curve, right? So we can calculate what's the dipole moment for the sphere. If you look at the expression, you just have to identify P divided by 4 pi epsilon 0 equals to this term here. Right? So that's what it is. I think I forgot the E0 in this expression. Yeah, there's some typo here, so times at E0 here, right? So that's what the dipole is. So the induced dipole, you have an induced dipole which is proportional to the applied field, right? So so outside the sphere, the field is that due to a uniform field plus a reaction dipole field. So if we look at the the field lines, we can plot that. The larger the permittivity, the more concentrated the field are going to be to the sphere. We can, pull all the lines inside. The lines tend to look to the region of higher permittivity. Right? So that's a solution. And also, notice that inside field is constant, right? So you see that this problem shows how to generate an exact potential function of the dipole field. We're going to show that in the next example in a more precise way. Suppose that you have that sphere we described earlier in one of the lectures. We have a sphere that is permanently polarized with the polarization vector P0AZ. Right? So in this case, we don't have applied field. So we don't have a linear medium as well. We have polarization is constant inside, and outside we have vacuum. Right? Okay, have vacuum outside. So now we have a constant polarization. We don't have a permittivity inside. So outside we have this constitutive relationship between D and E, and inside we have this other one. We don't have an epsilon, but we have this condition here, and this one is given, P is constant, okay? So outside we have a linear medium, we have Laplace's equation, no space charge, we have directly Laplace's equation, and in this case potential goes to 0 as r goes to infinity. Well, inside we don't have free charges, so we don't have the divergence of D inside is 0. And also this is an electrostatic problem, so E is irrotational, so the curl of E equals 0, so E can be written, this equation is wrong here, this is, sorry about that, there's a typo here, let me erase this thing here. I will write down here what are the pages that have mistakes. Page 8, and also the other pages, that first page there. We have two other errors here. Page 2, B goes to Z. We have page, the dipole, right? The dipole has a missing is 0 in the dipole. Where is it? Page 6. Page 6, we have to P is proportional to E0. And now, now page 8, we have this error here, page 8, expression A, which is wrong. So curl of E equals to curl of minus gradient of a function, right? I mean, if you have, because this is identity, so if the E field has has a 0 curl, it means that it can be written as a gradient of a function. So it can use this expression and put in here. Let's see what happens. Let me just move over there here. So it means, E field inside is minus gradient of a potential function, and the divergence of D equals to 0. D1 equals to epsilon 0 E1 plus the polarization. If you calculate the divergence, it's going to be epsilon 0 divergent of E1 plus divergent of P. So, but notice that P is constant and divergent of P equals 0. So it means that divergent of D1 equals to epsilon 0 divergent of E1 equals 0, and also by this relationship, right? If we plug in here, we have Laplacian of phi 1 equals 0. So it means even though the medium is nonlinear, the fact that the polarization is constant makes the potential to satisfy Laplace's equation inside as well, right? Again, we have a problem. We have a problem here. We have the sphere, right? And we have a z-axis, let's say. Okay, so we don't have dependence on phi, but the quantities depend on r and on theta. And if that's the case, we know that the potential is going to be that standard form, power of r, positive power of r, negative power of r, and Legendre polynomials of order L. So that's what they're going to have inside and outside, right? Very similar to the previous problem, previous example. And again, we are going to avoid singularities. We are going to cut this off. Okay? I mean, the L has to be 0, because otherwise we have something that blows away in the origin. And also, in this case now, as R goes to infinity, the potential has to go to 0. I'm sorry, I mixed. This is a solution outside, right? So this is a solution inside. So inside, BL has to go to 0. And outside, the potential has to go to 0 as R goes to infinity. So this term here has to go to 0. So those terms here will be eliminated, and we are going to end up with AL and DL, two constants to be determined. It's not difficult to find, again, right? The system of two equations, two unknowns, we have an infinite discrete set of constants, but uniqueness of expansions guarantees that several constants are going to be 0, those that are not associated with a homogeneous, with a non-homogeneous linear system. If you do that, you're going to have, let me see if it is correct. Yeah. So BL equals 0, right? And CL equals 0, as mentioned in this next page. So the solutions are like this. And then we have boundary conditions. Well, continuity of the potential, and the other one is normal component of the, I'm going to do separately here. So the boundary condition, we recall that one is the continuity, right, of the potential. So we can use expressions. The other ones is that normal D1, radial component at R equals A equals to D2 at R equals to A. D1 equals epsilon 0 E1 plus P. And D2 equals to, and D2 equals to epsilon 0 E2. And in turn, this is minus epsilon 0 nabla of phi 1 plus P. This equals to minus epsilon 0 nabla of phi 2. So it means that the continuity of the normal component will give me minus epsilon 0 d phi 1 dr at R equals to A. Then we have P dot R plus P AZ, P equals to P0, right? I have a constant P, I guess. It's PAZ dot AR, which is the projection of the polarization vector along the radial direction, equals to minus epsilon 0 d phi 2 dr at R equals 0. I'm just going to do this quick calculation here. This is P cosine theta. And recall that, unfortunately, I was using the same letter for polarization, which is P, and Legendre polynomial, which is PL. So let's not mix things, okay? So it's going to be this P here times this one, which is, I'm going to put a parenthesis here, P1 of cosine theta. Okay? So this P is not the same as that one. Let's not make that, let's not do that mistake, right? So you have those equations. So you can assemble the equation. I'm going to skip some of the steps here. We're going to have, we are going to have, you can assemble the sums something times PL cosine theta, right? You do we are going to have two sets of equations like this. I'm going to say combination. The constants that are different from 0 is AL and DL. So let's say that we have a linear combination, let's call L1 of AL and DL times PL cosine theta equals to 0. And another combination, this comes from the continuity of the potential. The other combination is a linear combination L2 of AL and DL times PL of cosine theta equals 0. I'm going to call let's call this L1. This depends on L, okay? I'm going to call this one L2. So a linear operator, a linear function, let's say. The only, in fact, not equals to 0. Not equals to 0. It's something like this. One of them is minus P over epsilon 0 times cosine theta, right? So we have one non-homogeneous equation for L equals 1, because this is P1 of cosine theta. We can equate the L equals 1 term to the same coefficient here. Then we have equation for L equals 1. So you have, so what happens is that we have L1 L equals 1 of AL and DL equals to minus P0 and L 2 of AL DL equals to 0. So this is a 2 by 2 system, non-homogeneous, right? So we can solve for AL and DL. We obtain a result. In fact, not for AL and DL. We have here, in fact, A1 and D1. So we have one linear system involving constants A1 and D1. So because this is a non-homogeneous system, we have solutions which are different from 0. The remaining equations for L different than 1, they are going to involve L1L L2L of ALDL, both equals to 0. So we have a homogeneous system for each L. So in this case, all the coefficients, because this is a linear combination of AL and DL, have two equations, two unknowns, homogeneous. So AL equals to DL equals 0 for L different than 1. So that's the solution of the problem. So if we solve it, the first, the equation for L equals to 1 is this one here. Okay, that gives a result for A and D. Okay, that's the result, and the other ones are going to be 0. So it means that the potential has only one component. It's not a series, but only one term of the series is enough to solve the problem, inside and outside. Inside, the potential is going to be given by, again, a function that is R cosine theta, because it's the P1 cosine theta times R raised to the first power. So inside, the potential is that due to a uniform field, right? Due to a uniform field. So the field inside, if you calculate minus nabla of phi, you have a field that is directed toward, I mean, P is like this, minus P direction, right? And if you use the constitutive relation, D1 is going to be on the same direction of P, right? D and P are same direction. E is in the opposite direction. So D is going to be 2/3 of P, okay? And outside, what happens? We have a characteristic of a dipole field again, right? Cosine theta in the numerator, square of the distance in the denominator. So that means that we have a dipole. The dipole moment we can, this you can put in the form P cosine theta divided by 4 pi r square. Then you can calculate P, and in fact, it's going to be the polarization times the volume, right? Polarization is dipole moment per unit volume. So the dipole moment is exactly that. So the sphere outside, the field of the sphere, the potential outside is given by that. So that's the field configuration. Inside, the field is like this, going down, right? So if you see, let me draw separately here. What is the sphere that is polarized like that, right? It means that we have surface polarization charges on the surface, which are like this, and minus here. So 0 here, plus here, right? And this gives a field that goes like this, uniform. So why do we have this residue here? Because that's the tip of the polarization vector, which has a projection on the normal. We know that we have a normal component of polarization charge density, which equals to P0 dot product with the normal that points outside of the sphere of the dielectric. So that's what you have. We have a function which is P0 cosine theta. So if you see how it behaves, that's for theta equals pi over 2, have a 0 surface density. Theta smaller than pi over 2, we have a positive density, and here we have a negative density. So that's what we have. And that's why the field points down like this, inside. And outside, the potential is that due to a point dipole at the center, right? It's as if we had a point dipole right in the middle. The potential outside is exactly that, is identical to that of a point dipole located at x equals 0. So a polarized sphere, a uniformly polarized sphere, is a perfect representation of a point dipole. It gives the correct potential outside. Okay? That's a nice example, a nice way to build or to simulate a point dipole. Just build a sphere and make it uniformly polarized. You have the exact representation of a point dipole. Okay? Very well. Let's go on. Well, let's take a look at that thing that we keep talking about. The Green's function is symmetric. Let's see in what conditions this is true. This is not always true, but in most of the problems it is true. Okay, but this is not very. This is important to simplify the solution of certain problems, but we don't have to use that property to solve certain problems. We did use that property to solve a couple of complicated problems, but we're going to show today that, first I'm going to prove that under what conditions Green's function is symmetric. And then we are going to solve a problem that I could use the symmetry property, but I'm not going to use it. I'm going to show how to solve the problem anyway. So Green's function, by definition, is that is governed by this differential equation for the Poisson's equation, right? We can, for instance, right, just notice the singularity is at the second argument, which is this one here. So if you put x1 here, the singularity is right there, x2 here, singularity is out there. So let's just do some tricks here to see what happens, how we get to the symmetry. Let's combine this special combination, the Green's function with singularity at x2 times Laplacian of Green's function that has singularity at x1. Then I subtract, I just exchange x1 and x2. Let's see what happens. The idea is to integrate in a volume, to transform this into a surface integral, and the surface integral is going to help me to identify the symmetry property. So why do we do the Laplacian? Well, because Laplacian is given by the delta function, minus 4 pi the delta function. And when I integrate in a volume, delta function just picks up the function at that singularity point, right? So let's do that. Let's integrate in a volume, okay? In what variable? Well, integration variable is x. x1 and x2 are fixed vectors, okay? So when we do the integration, then we end up with this minus 4 pi delta x minus x1, minus 4 pi delta x minus x2. Integration is in the x variable, right? So when I do the integration, I'm going to have x g of x1, x2, and here, singularity at x2, I'm going to pick up g of x2, x1. So that's the result we get, right? Now, at the same time, this integration can be transformed into a surface integral. We have done that before, right? It's just Gauss's theorem, in fact. If we play around, I demonstrate that in the review of the mathematical tools that we had in the beginning of the course. We can go there and review again. But this is just Gauss's theorem, okay? This divergence of gradients, right? Then we have a chain rule also that is used, right? When you do that, we have a function times the gradient of the second one. Then we subtract the exchanged combination. Use g for f and the normal derivative for the, in other words, g for f and g of the other argument for g, for lowercase g. Then what we have is that, I mean, what we had before is this thing here. So it means that this combination can be written in terms of surface integral that involves g of one argument, x2, the second argument, normal derivative of g of the second argument given by x1, and then the other term is just exchange the arguments x1 and x2, right? We get that thing here. Okay? So we have three types of problems. We have Dirichlet, right? We have Neumann, in which the potential is given at the boundaries. We have Neumann, in which the normal derivative is specified for the potential, right? We are talking about the Green's function that helps to determine the potential. But Dirichlet boundary value problem, we have a Green's function that handles that problem. Neumann's boundary value problem have a Green's function that handles that problem. Then have a mixed boundary value problem, as we did describe in a previous lecture. Okay? So if you have Dirichlet boundary value problem, you know very well that we choose a Green's function that has a that is 0. The Green function satisfies the Green's differential equation, which is Laplacian equals to minus 4 pi delta, right? And we choose a Green's function that is grounded, let's say, in the boundary of the domain. So if for this type of Green's function, g equals 0, then we have this thing equals 0 and this one equals 0. It means that this is equal to 0, or in other words, the Green's function is symmetric. Has that property. If you exchange the arguments, x1, x2, the function doesn't change, right? Let's move to Neumann's boundary value problem. What happens now, well, we recall that we talked about that before. We cannot set the normal derivative equals 0 in the Neumann's BVP. Cannot do that. The most that we can do, I mean, we can do a lot of things, but we cannot set equals 0. Cannot set equals 0 in the whole boundary, the whole domain. You can put some parts equals 0 derivative if you want. Okay? But one interesting choice is the normal derivative equals to a constant given by this value. And we saw that when we did that, it means that the potential that we solved, the solution is going to have an extra term, which is the average value of the potential on the boundary. If we choose that the derivative is constant, which is minus 4 pi divided by the area, the total boundary area, or the total area of the region in which the normal derivative is not 0. For instance, okay, I can have a boundary like this, and you have a portion of the boundary, this red one, like this. Okay, let's call this sigma 2 and this sigma 1. I can make a Green's function if I want to, such that dg, the normal coordinate at sigma 2 equals 0, and I can choose, for instance, dg dxn at sigma 1 equals to minus 4 pi divided by this area sigma 1 here. Okay? If I do this, the potential is going to have an extra term, which is going to be an average value. Can do that too. Okay? But let's assume that I picked a constant normal derivative, and I choose that. So it means that the difference of the g's with exchanged arguments is not going to be 0 now. I'm going to have one term. I already factored out the normal derivative, which is constant. The 4 pi already canceled, just do that calculation. So this gives me a function of only x2 after I integrate on the surface. And I have a similar function here, which is the same thing, right? Calculated at x1. So it means that the difference of the Green's function when we exchange arguments is not 0. But if you build the function g bar equals to g minus f, okay? So you see here that I can move the f to the first member here. I can make g x1 x2 minus f, minus f of x2, right? Then we have one term. On the other side, I'm going to have equals to g x2 x1 minus f x1. So it means that these functions are equal. So if I build this function g bar, by definition, equals to gxy minus f of y, this function is symmetric. Not the original Green's function, but this, let's say, pseudo Green's function is going to be symmetric. Okay? So rigorously, the Green function is not symmetric, but I can construct a pseudo, let's say, Green's function that's going to be symmetric. Okay? We might use that artifact in some problems. It might be interesting to use it. I mean, the symmetry is nice to use to simplify some complex problems. So you can reduce the algebra a little bit. But it's not mandatory to use the symmetry property. Symmetry property is nice to have some elegant solution of certain kinds of properties. So in summary, for Neumann's boundary value problem, Green's function is not symmetric, but G bar is symmetric. Okay? And going back now to mixed boundary, another mistake here, BVP, right? Page number 15, BPP, another mistake, I have to fix it. Well, so if I have now a mixed boundary value problem, well, what we do, we assume that the potential let's say that we have two surfaces, right? Let's assume we can have a very complex domain, border of the domain. Let's assume that for simplicity, without loss of generality, that we have the boundaries broken into boundaries, sigma 1 and sigma 2, okay? So, I mean, it means that sigma 1 union with sigma 2 is the total boundary, sigma, and the intercept is the empty set, right? So what we do is this. I mean, we assume that the equivalent problem is the potential is given at sigma 1, right? So the potential is given at sigma 1, and the normal derivative is given at sigma 2. So what we do is to use a Green's function that is 0, right? Is 0 at sigma 1 and has a 0 derivative at sigma 2. I'm sorry. Is a non-zero derivative at sigma 1, right? So I choose G equals 0, but the derivative is not 0. In the other surface, I choose the derivative equals 0, and is not mandatory that the G is 0. So what does it mean? That the product G times the derivative is always 0. So so if you have this combination, right, G not 0 and the other surface and normal derivative equals 0, so it means that the product G times derivative is always 0, whatever surface you choose, right? If we have that choice of Green's function, I mean, in parts of the surface G is 0, that's where the normal derivative of the potential is given. On the other part, the normal derivative of the Green's function is 0, in other words, when the potential is given. Okay. So then we have, it's the other way around. I mean, the normal derivative of the Green's function is 0 when the normal derivative of the potential is given. Okay. So if we do that, so then it doesn't depend on the potential value. So if we do that, it means that the product is always 0, and again, Green's function is symmetric. So that's the full proof of the symmetry property of Green's function. Green's function is symmetric for mixed boundary value problems, and for divisionally boundary value problems. Is not necessarily symmetric for Neumann's boundary value problem. Okay, let's go now to the final part of the lecture. We want to discuss the method of image for true dielectrics, and let's assume that we have a point charge inside of one of them, the dielectric 1. Okay, so what's going to happen here? How do we solve it? What intuitively what's going to happen is you're going to have an image charge that gives a result in the region below. The image charge cannot be in the region below. If we want to solve the problem in this region here, the image charge has to be put outside, has to be placed on medium 1. So the image charge is only useful to solve the problem in region 2. And in the same way, I mean, the solution in region 2 has to be due to the charge and the image charge located in region 2. Right? You can do that. Could play with that and find those values and location of those image charges. So we're going to do a little differently. We are going to solve it, right? We have to solve the problem in which the potential is given by this differential equation, Poisson's equation, in region 1, right? The delta function is that due to a singularity on the z-axis at a distance d. So you can write the delta function like this. You can easily, it's easy to find by inspection that this gives the correct value. If we integrate on a volume, it's gonna be 1, right? You just use the dv equals to r dr. The phi integral gives 2 pi, cancels that 1. R cancels R, then you have a 1, right? So those functions, I mean, we don't have, you have a azimuthal symmetry. Those functions depends only on R and Z, okay? So we can expand those functions in the normal modes, but you see that the domain in R is infinity. So we can, I mean, just do this thing here. I can always write, right? If we have something like this, equals to either a delta function or equals 0, let's say, can always expand. We have unlimited domain on the R direction. Well, I can, so no dependence on the azimuthal coordinates, right? I could have something like this. Sum m equals to minus infinity to plus infinity, exponential for jm phi. Then I would have something like this. Not like that, but I would have something like, just put it down back here. I would have some Bessel Fourier integral, right? I will have something like that. Integral in decay, a coefficient, right? A m of k, jm of kr. Then I would have a dependence exponential of minus kz. I would have something like that. If I have an unlimited domain on the upper hemisphere, then I have some sort of integral like this. That's what we would have. Okay. I'm not going to put the integration limits. But you see that m equals to 0 because no dependence on the azimuthal coordinates. So I have only one term, which is m equals 0. So phi equals to a Fourier-Bessel integral, okay, which is something like this, am of k. I can have combinations of these functions here. I can have exponential minus kz, or exponential of kz. I have to use the proper solution that doesn't blows up if I have an unlimited domain, okay? So I would have something like this: a0 of k, j0 of kr, exponential of minus kz, or plus or minus. So the function can be always expanded when you don't have azimuthal dependence. You can combine those two things in a function of z, gk of z, j0 of kr. So when you have unlimited region, if you have a potential in which the domain is 0, smaller than r, smaller than infinity, and z also, you have the whole domain, right? You have to use something that depends on z, a combination of positive and negative exponentials. In one domain you might not have the positive or the negative exponential, on the other you can. And you only have the j0 function that appears, okay? So because of this, you can expand the functions in both regions. Region A, which is the upper part, it's called this region A, okay? This is region B. Region A is z larger or equal than 0. Region B is z smaller than 0 or equal. So in region A, we are going to have a certain function. We have to be careful, okay? Notice, every time I have a singularity like this, the function that is a z-dependent function doesn't have continuous derivative because of the delta function. The function has continuity, but doesn't have a continuous derivative because of a z equals z, there is a singularity. So I have to use a function that has this double behavior, which is continuous, but has a, some sort of discontinuous derivative on the singularity. So the function in the upper region, region A, is going to be represented by a function of z. This function has combination of exponentials, real exponentials, times j0, okay? And in the lower hemisphere, region B, the dependence, you have a coefficient, ak, it's a constant but depends on k, and the exponential that decreases as z goes to minus infinity. So I use just explanation that doesn't blow up as z goes to minus infinity. So this is a combination of exponentials, plus or minus kz, but the minus kz blows up, so I just don't use it, just use the plus kz. Also, the jk has this behavior here, right? Has to go to 0 as z goes to infinity. Well, we are going to use this property here. This is the completeness of the delta function. Where does it come from? Let me see if I can find it here somewhere. I think I have it here. Here. It comes from this relation that we derived in lecture 10, I believe. Right? This is a completeness relation. You have a product of two delta functions having different arguments, k prime and k. If we integrate in one of the arguments, which is r, then I have a delta function on the other side. So I'm going to change variables. I'm going to use this thing here. We copy. Let's use this. Let me go here to the end. Let me put it back here. So I'm going to make, first of all, I'm going to use, this is valid for any value of m. I'm going to make m equals to 0. First thing I do. So I have integral from 0 to infinity. prime, right? R equals to 1 over k delta of k minus k prime. Well, that's the first thing I do. The second thing I do is to make k prime equals 0. So k prime equals 0, so I have integral from 0 to infinity dr r j0 of kr. Then I have j0 of 1 equals to 1, Bessel function of order 0 at the origin equals to 1. And here is delta of k equals 1 over k delta of k, right? So now the only last thing I have to do is to exchange k with r, right? So we're going to have integral from 0 to infinity of dk times k, right? j0 of kr equals 1 over r delta of r. Okay? So that's the relation we get from our completeness that we have derived in a previous lecture. So in dielectric 1, which is the upper region, we have a delta function which is due to the charge. We're going to now use that expansion. So in the upper region, we're going to have Laplacian of phi 1. That's the density function that we have, right? And then we expand this function here as this one, right? And we keep the delta function in z. And then we rearrange. That's what we get, okay? And now we are going to expand the Laplacian in cylindrical coordinates for the case in which there is no dependence on the phi coordinates. So if we do that, okay, let's do that, and let's use the solution in the upper hemisphere because we want to solve for gk. We don't know the solution. So we're going to use the expansion for the potential in the upper hemisphere, which is given by this Fourier-Bessel integral here. And then you work on the details of that calculation, okay? So if you rearrange things, you are going to identify Bessel's differential equation. Okay? We can use that condition. We're going to have something like this taking place. So after we rearrange everything and use the condition on Bessel's differential equation, we have a differential equation involving the gk function. And again, recall that we have an expansion. You have to look this as being an expansion. The integral is like a sum, right? Term by term of the expansion. The coefficient of J0, which is this one, has to equal the coefficient of J0, which is this one here. Okay? K times delta Z minus D. So we have a differential equation that has to be satisfied by gk. So gk is like a Green's function in one dimension. Okay? But this is not a simple, Green's function in which the Green's function is 0 or the Green's function is 0 at infinity, but not at z equals 0. So we are not going to use symmetry here. Okay? But we are going to solve it. So how do we solve this equation here? As traditionally we do. We make z different than d, and we propose a solution for z larger than d and another for z smaller than d. We find the general solution. Then we handle the singularity by integration around that singularity. Okay? That's what we do. So that's the function. Then we make z different than d, okay? So that's the differential equation. This is a very simple equation that has exponential factors as solutions. For z larger than d, we have acceptable solution, which is a decreasing exponential, right? We have a coefficient. And for z between 0 and d, because we are in the upper region, we have a combination of positive and negative exponentials that are allowed. Okay? So notice now, how many constants we have in the problem? Let's enumerate, okay? In the upper region, z larger than 0, then we have two subregions. 0, z larger than 0 smaller than d, and z larger than d. Here we have a solution that we called gk equals to bk minus kz, and here we have gk equals to ck plus dk, put this back here, exponential of minus kz. And in the region z smaller than 0, each corresponding Fourier component is of the form z smaller than 0. We have a solution which is of the form bk exponential of kz. So how many constants we have to solve the problem? We have 1 constant, 2, 3, and 4. How many equations we have? Right? Well, at z equals 0, we have continuity of the potential, 1 equation, right? The other is continuity of the normal component of the flux density vector. 2nd equation, right? We need 2 more. This gk function here in the upper hemisphere is a type Green's function, right? But notice the Green's function, in fact, the solution in the region 2 is a combination of gk functions like this. But notice that each gk function has to be continuous at z equals d, right? Because we have unique expansions. The expansions have to have the same value at z equals d, calculated from the upper region, from the subdomain that's z larger than d, or for the subdomain from z between 0 and d. So these functions have to be continuous. So gk, that's the 3rd condition that is going to tie, b, c, and d. So one is gk is continuous at z equals d. 3rd equation, right? And what is the 4th equation? Well, the 4th equation comes from the differential equation, which is this one here. We have to handle the singularity. And how do we do that? We integrate across the singularity, z equals d. When we integrate, we are going to have a value here. It's going to pick up a value at z equals d. And here, this thing here is not going to contribute. There's going to be no difference if you integrate. As the integration region is very small, this term contributes to 0, but this one gives a discontinuity in normal derivative. Okay, so that's the 4th equation that we needed. So 1 equation, 2 equations, 3 equations, and the 4th equation is using the differential equation. So it means that we have 4 equations to 4 unknowns. And then you have all the details in the class notes, okay? And we can solve for the 4 parameters. And specifically for the discontinuity, you can see equations 13 point, I think 13.7 gives that condition. And we integrate, I'm just going to show you some points on the derivation here. And then integrate the differential equation, have this condition here. I mean, this term here gives negligible contribution in the limit as the increment, you know, epsilon is the difference above and below, epsilon minus epsilon. So this is going to be a contribution which is g at the z equals z times epsilon, times 2 epsilon. In the limit as epsilon goes to 0, this goes to 0. Okay? So I have this is the result of the integration in the delta function, and we have a difference of derivatives. So every green function has this property that we have always to remember, okay? When you have that singularity, the point of the delta function, the green function is going to have this behavior here, okay? So we have continuity of the function and discontinuity of the derivative. We have some sharp, you know, discontinuous connection between the two sides. Connection and discontinuous derivative connection. There's no smooth connection. It's a sudden change of derivative. It's one like this, the other like that. Okay. So every green function has this behavior here in the singularity. So that's what happens here. I mean, derivatives has a discontinuous step there. So let's have those equations, and we can determine then the constants. I have some lengthy calculations. I mean, this specific green function has a symmetry property. In fact, you could use that. You could save some time, you know, use the symmetry property. But it's not very evident that the symmetry property works in this case. Okay, this is a mixed boundary value problem. So, because of the demonstration we did before, in fact, the Green's function has a symmetry, and we could use that to solve. So the solutions in this 13.19, 13.20, these are the constants, you know, after we determine, I mean, the solution depends on AK on the lower hemisphere, and the GK function is something like this, on the upper hemisphere. And well, there's lots of algebra here. You see, we have this property in the upper hemisphere. G is a Green's function for a mixed boundary value problem condition. You're going to notice that symmetry property coming up. We could have saved, you know, that's just a remark here. We could just have saved time if we did use the symmetry property. But I mean, I just want to show you that is not necessary to use it. You can use just the continuity of the Green's function at the singularity. That can be used as well. Okay? So let's keep that. So after we complete the problem, you can just write the potential in this form here. This is the Q originally given. I have defined here a Q prime, capital Q prime, and a capital Q2 prime. These are obtained from the solution of the problem, okay? So these are the Q prime capital, Q prime, and Q2 prime. Well, if we use the expansion of the inverse function, these are in fact expansions of the inverse function. These are things that we did before, okay? I mean, the expansion of the inverse function can be written in this form when you have symmetry, azimuthal symmetry. If you put the x prime on the z-axis, they're going to have azimuthal symmetry, then have this type of expansion here. Okay, so it's very easy to recognize these are inverse functions. Okay, so the potential in the upper hemisphere has two inverse functions arising, and the potential in the lower hemisphere has one inverse function, and those inverse functions are determined by the charge and by those q prime and q2 prime fictitious charges that we call the image charges for this problem here. So after you do that, you see that the potential on the upper hemisphere is that due to a point charge located on the original location, which was given DAZ, and it's as if we had an image charge q prime in the distance in the lower hemisphere symmetrically located at the distance d. Okay? At the same time, the solution on the lower hemisphere is that due to a image charge, second image charge, on the upper hemisphere located at the same location of the original charge. Okay? So in the lower region, it's as if we had a charge q2 prime only. In the upper region, it's as if we had that original charge plus a fictitious charge in the lower hemisphere. These are the charges. Those are given in terms of this parameter epsilon 1, 2, which is the ratio, epsilon 1 over epsilon 2. And you notice that if epsilon 1 is larger than epsilon 2, this number is larger than 1, and then q prime becomes negative. I mean, that is not, I mean, q2 prime is always the same sign, has always the same sign of q. But q2 prime has the same sign. But q prime, which is the charge that is the image charge to solve the problem in the upper hemisphere, this might change signal depending on the dielectric relative permittivity, right? So that helps us to draw the field lines, to have an idea on how the field lines look like. Okay, this is for epsilon 1 larger than epsilon 2. It means that in the region, okay, in the region, the upper region, the q prime charge is negative. Okay, q prime times q has a negative sign. Let's assume that q is positive, so q prime is negative. So the problem in this region here is that due to q and q prime, so the lines are going to curve toward, you know, toward q prime, like this, right? On the other hand, the solution in the lower hemisphere is that due to a fictitious q2 prime here, which is always the same sign, and it's as if the field lines were like this. See? So they are radial lines that would, if you extend them, they would end on the point charge on the upper hemisphere. Okay? So that's the curvature of the lines. I mean, epsilon 1 larger than epsilon 2, we have to bend like this, then go like that. On the other hand, if we have epsilon 1 smaller than epsilon 2, then in this case, q prime, which is the image charge in the lower hemisphere, is going to have the same sign as q, and you're going to have a curve that goes like this because it's a repulsion, right? Two charges of the same sign, the field lines will be curved, would bend away from the fictitious charge there, right? But on the other hand, the lines here are still the same, radial lines, like before. Okay, so that's how the line look like in this case. So this is a nice illustration of solving the the problem of a point charge embedded in one dielectric next to another dielectric, and how the field lines bend depending on the relative size of those dielectric materials. Okay, permittivity, in fact. So I think we close here with this illustration, and I hope to see you next time. Till then, bye-bye.